All right, so this is section 15.7B, video 2. All right, so as I mentioned in the previous video, this surface would have been kind of difficult to picture, so I did provide a sketch. I'm also going to show you a three-dimensional manipulative of this thing because seeing the projections in this is a little bit difficult. What we see three-dimensionally and what you see as a three-dimensional projection can honestly take well, your eyesight can play tricks on you, basically, is what it comes down to. So a couple things that we should know. First of all, in this case, they gave us the first integral. Okay, they gave us the first one, so we have to find the other five. In this case, they gave us one where they did dz, dy, dx. So in this case, the x and y plane is going to be our two-dimensional projection to start with. A couple things that you should notice. What they've done is they've said, by looking at this, you know that z is going to vary from 0 to 1 minus y. If you look at the plane, and again, this is where it gets a little bit difficult, the z goes from 0, which is the xy plane, so someplace down here, up till the point where it hits someplace on that flat plane. It's z equals 1 minus y. That's just a plane. Okay, that's a flat plane. So z is going to vary from 0 to 1 minus y. It might help, given the original one here, if you actually write that out as a domain. So z is going to vary from 0 to 1 minus y. And then the second piece says that y is going to vary from the square root of x to 1. So y is going to go from the square root of x, and that is the lower bound, to 1. So y varies from the square root of x, which is that piece right there, out to 1. And then x is just going to go from 0 to 1. I'm really not going to draw that one, but you can see that the x value goes from 0 out to the 1 that would be right there. I am, however, going to write it. So x is going to vary between, oops, not 0 is going to vary. X is going to vary between 0 and 1. Okay, this might help. We'll see with how we're going to figure this thing out. So the first thing, like I said, the first thing I want to do is, because we have to write the other five, I'm going to do the one where the z is still the innermost integral, because it seems like that's the easiest one, since it's the one they gave us. So I'm going to draw the xy projection. Okay, the xy projection is what it would be if you were standing someplace up here and looking straight down onto this thing. So this is where it gets a little bit difficult. Now, if you can see this, this is great. And I'm still going to show it to you in a manipulative anyway. But this one's not so hard to see, because if I look straight down, what we should see is what I'm tracing right here on the xy plane. This would be your xy domain, or your trace, your two-dimensional trace. That's what it should look like. So let's see, I know I'm going to start at the origin. I know that the x value finishes at 1, but it looks like this point right here, which is the point 1, 1, 0, is where the curve finishes. So it's going to be at 1, 1 on the xy plane, and then it's going to have this kind of a curve because it is a square root of x. So that's kind of what the square root of x looks like. And then y equals 1 is just going to be that piece right there. So it's the space in between those two curves. So the one that they've given us was dy dx, which was a type 1, so we need to define it as a type 2 for ours, which is going to go this direction, which means that your x is going to vary from a curve to a curve, and y is going to go from a number to a number. So let's go ahead and set this one up. So we're going to have our triple integral. The easiest part here is going to be the z, because they've actually already given that to us. And again, they're just calling it f, so I'm just going to call it f here. dz. They gave us the innermost bounds was going to be 0 to 1 minus y. That's what z varies from. That's not going to change. But now we're going type 2, which is going to be dx dy, because they gave us dy dx. So we know the y, we can actually fill that part in first if we want to. We know y is going to go from 0 to 1. It's got to be from a number to a number. The x is going to go from the leftmost one, which is y equals 0. And if you kind of look back up at your domain, up until you get to this curved function. What that says, though, however, because we know that that's part of this right here, we need to solve that equation for x. Well, that's just squaring both sides. So x is y squared. That's actually going to be your rightmost bound, y squared, because you have to put the x and y relationship into terms of x in this case, since it's going from a function to a function. So there are your bounds for the second of the two. Second of the 6. We've still got 4 more to go. All right, I'm going to try to do 2 more of them on this page, and then I'll probably have to squeeze or not squeeze, but I'll have to probably put the last 2 on the next page. Okay, so now it doesn't really make any difference which projection we do. So I think what I'm going to do is I'm going to probably try and project this thing into the YZ plane. It doesn't matter. One way or the other, I'm going to have to show you the manipulative here to really get you to see what's going on here. If you can actually visually see this, and again, this is kind of where your mind can play tricks on you. We'll figure out the X part in just a second. But I want to see if we can figure out what this thing looks like as a 2-dimensional projection into the YZ plane. So this is Y, this is Z. So one of the things you might want to do is just kind of figure out, okay, this upper piece right here is when Z equals 1. So I know that that's going to be part of it. So there's Z equals 1. And then this piece down here, which is really going to be so again, this would be like if I'm standing right there. I probably shouldn't put an X right there. I'll put a dot. I'm standing right there, and I'm looking at it in that direction. So I would see this as my other endpoint, also 0 down at the bottom, because you're going to see that. But then all you're going to see is this piece down here, which, again, that's at the point 1, 1, 0. So if I project that down into this plane, it's going to be when y is 1 and z is 0. So the question is, what does it look like from there? This part right here makes it look like it's curved, and the question is that the case? So let's take a look at the manipulative that I said I was going to show you and see if we can figure that out. All right, so here is CalcPlot 3D. And what I've done is I went ahead and I put the sketch in here. Now, the only thing I didn't do was shade everything in. 1, because I didn't know how to. And 2, I just didn't feel like taking the time. But you can see this is exactly the same thing that we had. So the plane, the slanted plane, z equals 1 minus y, is basically here in red. The blue part on the bottom is the projection down into the xy plane. And then what you've got here with the kind of the yellow dotted, black dotted kind of line right here shows you, and maybe you can see it better here, shows you visually what this thing is going to look like as a projection. So really, if you just trace what's on the on the ZY plane, YZ plane, it's going to look like this over here, and then all you're going to see is that straight line right there. So it's going to look like a triangle. And to show you that, let me go ahead and turn this thing. Hopefully I can do this. Turn it to the right just a little bit. There we go. So I'm trying to get it lined up here. It's not the easiest thing to do. But there's basically the idea. I don't want to push it up any further, but if you did, it would look like just a triangle. Okay, and again, you might, because if you're looking at it this, say, oh, it's going to look curved from there, but it's not. It's actually just going to look like a triangle when you set it. So if we were looking at it from that perspective, this is all we would see. All right, so now let's figure out how to set up these integrals. So this is going to be our third and fourth integrals. As a matter of fact, I'm just going to write both of the sets down. In this case, dx is going to be the innermost piece on both of them. And then we'll either do a type 1 or a type 2. So let's figure out what x is going to vary from. All right, so x is going from, back into our three-dimensional shape, x is going to go from this curved piece right here. I'll put it in, I don't know, red. It's going to go from this curved piece right here. Nope, I apologize. That's not right. X, I was getting ready to do Y. X is going to go from basically what would be the YZ plane out to that curved piece. So it's going to go from someplace on the YZ plane out till it hits this curved piece right here. Okay, and that curved piece is defined by y equals the square root of x. So we know x is going to go from 0 out till it hits y equals the square root of x. But again, you want to solve that in terms of x, which we've already done. So it's going to go out to y squared. And it's going to be the same in both cases. And then we just got to figure out, okay, the rest of this is actually pretty easy. We're going to do this in terms of type 1 or type 2 first. I'll just do type 1 first, which means that z is going to go from function to function. So that means z is going to go from 0. Here we're going to do dz dy. So z is going to go from 0 up to this line. Well, that line right there, let's see, we've got a y-intercept of 1, or excuse me, a z-intercept of 1. So that line is going to be 1. Slope is going to be 1, so 1 minus y. So z is going to vary from 0 to 1 minus y. And then y is going to go from number to number, which is 0 to 1. And all this makes sense because the only variables that I have in the innermost integrals are y's. That's the last thing I have to take the antiderivative of, so it will work. Let's change the order. So we'll do a dy and then a dz. So instead, we're going to go this direction. So this time, y is going to go from function to function. So y is going to go from 0, which is the z-axis, up to that line. But that line had the equation z equals 1 minus y. If I solve that for y instead, you're just going to get y equals 1 minus z. And is that okay? Yes, it is, because z is the outermost integral. So I'm just going to have terms of z left over. And then, of course, z is going to go from 0 to 1. All right, so I think I am going to just move this just for space purposes to the next page. And again, I'll go back to the manipulative to show you what this is going to look like. But now we're dealing with the xz plane. So the xz plane. So let's take a look at it from the perspective of the manipulative. So the xz plane here means that I need to look at this thing. Probably be best to look at it if x is positive. So I need to try and rotate this thing to the right if I can. This is the hardest thing to do. If I had the keyboard, it would be easier, but I don't have the keyboard set up with it. So if I rotate it so that all I can see is the xz plane, keep going, come on, keep going. I'm trying here, I really am. Boy, this is difficult to do. All right, I think that's about as good as we're going to get there. So that looks like the projection into the xz plane. So what you can see visually, if you were standing, I will go back to the original drawing, but if you were standing, basically, I guess from the y-axis, that's what you would see. So if we go back to our original sketch, we were standing on the y-axis from someplace. Let me use a different color. Let me use purple. If we were standing like over here and looking at it in that direction, or looking at it in the other direction from this way, but it would be backwards if you were over here, that's the shape that you would have seen. So if I'm not mistaken, just sketching it real quick, it looked something like this. I know that those bounds are going to be 1s. It looked kind of curved like that. and that's the projection that you would see into the XZ plane. So we'll just say that's the X, that's the Z. Okay, so let's go ahead and set up two sets of integrals. Of f. So this is first going to be dy, so we do need to know what y is going to vary from. All right, let's go back to the original. So y varies from the square root of x. Let's see. Y is going to vary from the square root of x up to 1. At least that's what it looks like. Nope, I apologize. Y is going to go from the square root of x. This is the hardest one. Y is going to go from the square root of x, which is this curved piece here, up till it hits this plane. And it's obviously going to change depending on where on the plane it hits. So it's really going to go from the square root of x to 1 minus z, because I got to solve that for terms of y. So it's going to go from the square root of x to 1 minus z. I have to go back here and write that before I forget it. From the square root of x as the bottom bound to 1 minus z as the upper bound. And remember, this is the one that it's okay to have both variables in, because I'm going to have to use both variables in the next two integrals anyway. All right, so then we're going to have to do either a type 1 or a type 2. So if we do a type 1, that means that z would be the next piece, and then x. Okay, x is going to go from 0 to 1, because we know both of those values are 1. That's the easier one. Z is going to go from 0 up to whatever we call that particular curve right there. Well, let's see. The original curve right there, that is defined as z equals 1 minus y. But we can't have a y left over in our function. The good news is that I also have that y is the square root of x, and that's from the previous page. Okay, those are part of your bounds. So what I can do is I can replace the y value with the square root of x, so that I can say that that function can be written as z equals 1 minus the square root of x. So that's going to be the upper bound for z, and then that's okay, because now all I've got is an x left over, which is my last integral. All right, and then we've got one more way, which is going to be to do dx dz. And again, the z part in this case, because it's going from number to number, is the easiest one. That's just going to be 0 to 1. And then x has to go from here, which is 0, out to the function. Well, we do have something in terms of z now, so we just basically have to solve that function right there for z. So if we do that, let's see, if we add square root of x and subtract 1, we're going to get, subtract z. We're going to get that, and then we got to solve for x, so we have to square both sides. So we would get 1 minus z quantity squared. So that's going to be your upper bound. All right, and as I said, these are not easy to do. Okay, these are very, very visual things to be able to do. So we'll come back, and I am going to try and run through them just a little bit quicker. I think I've got one more to do for setup purposes, and then we've actually got a couple of actual problems here, and you do not need to do the problems using every single possible method, but I just want to show you how the setup is going to work with one more of these. So probably be one more video, maybe two, because the last problem takes a while, but try and get into one.